Okay, ji, Bismillah Rahman Rahim. Today we're going to be covering low-level programming, and this is part of your paper 4. And we have studied low-level programming, assembly programming language in paper 1. In fact, not in one chapter, we've done it in 2 chapters. If you remember, in paper 1, there is a topic regarding assembly language on its own, and then we're using assembly language programming techniques in the domain of your monitoring and control systems and bit manipulation, so on and so forth. So if you need to revise that, the notes and links are available, videos are available. You can go through that for paper 1. But right now we're going to be focusing on low-level programming language for your paper 4 preparation. Now, paper 4 low-level programming basically involves us applying assembly language in the context of applying your or implementing your program structures. So that means we should be able to apply loops and selections and even linked list and data structures like so in low-level programming. Now, let's first of all, let's go through what just a quick recap of the opcodes and operations, basically the instructions that we'll be using in assembly language. We've already done this in great detail in paper 1, but just a quick recap just in case we need a refresher for this. So basically we're using assembly language here, and for assembly language, the instruction format involves an opcode and an operand. We studied this in paper 1 as well, that not all instructions, there can be some special instructions that don't have operands. For example, in and out, there are 2 instructions that don't have operands, whereas opcodes is a must. All instructions have opcodes. So a complete instruction, most instructions are completely defined by the use of their opcode as well as their operands. Okay. Now, this representation that we see in front of us, this is known as a mnemonic, as discussed before. And basically, it's just a 3-letter representation that is sort of an abbreviation of what's happening. So we'll look through these in mnemonics and try to understand what they mean, so that when they come about in our code, we can make sense of what's happening. So anyway, for example, this first one is LDM. We're just gonna quickly go through them so that we remember what they are. So LDM, basically LDM means load using immediate addressing. So whenever we're talking about loading something, that means we're bringing data into our general purpose register, which is your accumulators. So when I say load, it means loading the data is becoming into your accumulator register. So LDM means immediate addressing. So by LDM, we mean that this opcode is not actually an address, even though the term has immediate addressing, but this is not an address, this is a value. So that means this value, as it is, whatever it is, will be sent to the ACC. Now, 2 things to note here is, first of all, you can see the mnemonic states that it's LDM, so we can tell that it's immediate addressing right there. Second thing, we notice that this is not an address, it's a value. And third most important thing is that you notice that there's a hash here. So if I mention a hash symbol here, it means this thing should not be treated as an address. In fact, it should be treated as a value. Similarly, if you can see here, this means LDD. Now LDD means that this is actually an address now. LDD is load using direct addressing. So what it means is that the contents of this address, whatever the address is, the contents of this address are to be sent into the ACC directly, direct addressing, simple as that. This is known as indirect addressing, LDI. So what that means is that this is an address, yes. The contents of this address are another address, and the contents of that address are to be brought into the ACC. So this is indirect addressing. This is an address. The contents of this address are another address, and the contents of that address will be brought into the ACC. This is direct addressing, LDD. That means this is an address, and the contents of this address right here will be brought into the ACC. We have to access these contents indirectly, where we can do that directly with direct addressing. This is index addressing. Now for index addressing, I have to make use of the index register as well. So this address mentioned here will be my base address. I will combine this base address with the value stored in my index address. I will add it actually. So this address coupled with the added with the contents of my index register will make a new address. The contents of that new address will be brought into the ACC. So let's just say if my address is 100 and my index register says 2, then actually I'm talking about the address 102, and the contents of 102 will be brought into the ACC. Similarly, we got LDR. This means I want to load using immediate addressing. But this time, instead of the value going to the ACC like it was going for LDM, LDR means the value will be going to the index register. So that's it's immediate addressing. We know this how that we can see a hash here. So this is a value. It's not immediate addressing. And secondly, since the mnemonic changed, before it was LDM, now it's LDR. That means the contents will be not sent to the ACC as they were doing in the LDM. They will be sent to the index register. And this value as it is will be sent to the index register. As it was the case for the immediate addressing, that this value as it is will be sent to the ACC. So here, now this is what store is. It starts with S, storing. Now storing procedure means storing is basically the reverse of loading. In loading, data is brought into the ACC. It can be brought in from some address, or it could be some value that I'm bringing into the ACC right away. On the other hand, when I'm storing some data, storing means that I am taking data from ACC back to a memory, for example. So in this case, say storing at this address means that I will take the contents of my ACC and I will bring it to this address. I will save it to this address. So it's the reverse process. It's the reverse of load. So I will take the contents of ACC and I will load it in this address right away. Okay, by the way, when a store process takes place, store operation takes place, the contents of the ACC are simply copied through this address. It does not mean that they're moved. So if I'm bringing that value into this address, the value still is present in the ACC. So it's just a point to note that we may have to use that exact value in a further instruction. So you don't need to load it again. It's still there. It's still in the ACC. So basically it's being copied here. Now this is STX. As LDX was index addressing, using index addressing, we were loading a value into the ACC. Here we will use index addressing, but this time we're loading a value from ACC or storing a value from ACC into an address. Now what we're doing is that we have this address. We will add this address value to the contents of the index register. That will bring up a new address. Then I will store the contents of the ACC to that new address. Similarly, as we saw load using indirect addressing, we have store using indirect addressing. In this, what we're doing is that this is an address. The contents of this address will also be an address. And I want to store the contents of my ACC to that indirect address. Not to this one, but to the address that's stored inside this address. I want to store my value to that address indirectly. So it's basically the opposite operation of my LDI. Okay. Afterwards, we got some opcodes that go around like ADD, increment, decrement. Now again, there's a slight variation of opcodes here. As you can see here, in this sequence of opcodes, my opcodes are followed by either an address or some value if it's an immediate addressing. Here also I'm using an address, but now we can see another type of instruction in which the operand is no longer an address as it was before, and neither is it a value like we've used before. In fact, it is a register. As you can see here, there's a register right here. So this is a new type of instruction. There's a different type of instruction in which my opcode, my operand can possibly be also a register. Okay, let's look at add first. Now what this does is add opcode takes the contents that are stored at this address and adds them to the contents of ACC, and the result will be stored back into the ACC. So again, I will take the contents of this address and I will add them to the value currently stored in the ACC, and I will store the result back in the ACC. So for example, my ACC has the value 5 and this address has the value 6. So when this line runs, 6 will be added to 5 and the result 11 will be stored back in the ACC. And one thing to note here is that ACC at a time can have only one value. So as soon as I send something to the ACC, the previous value is overwritten. So that means the contents previously of ACC will be overwritten once I store the sum or the result of this addition process. Now, what does increment, INC mean? It means increment. Now, what does increment do? It simply increases the value by 1. So if I have a mnemonic of increment, it has to be followed by not an address or a value, but it has to be followed, or it can be an address, but in most examples that we see in your paper, they are mentioned with registers. So now if I have a register here, my increment will simply do what? That it will increment the contents by 1 of this register. So if I say INC ACC, that would do what? The contents of the ACC will be incremented by 1. Same thing goes for decrements. I can, if I will mention a register name over here, so it could be both ACC or IX. Afterwards, decrement of this register over here will cause the value of the register to be decremented or reduced by 1. This is basically the arithmetic operations, and there's also subtraction as well, and that's mnemonic is SUB. So just mentioning that over here, we can use sub. In the exam there has been sub as well, so it goes like this. We got sub, and that would be mentioned along with the address as well, like before. So we got an address. Now what this does is that it takes the contents of this address, subtracts them from the contents of the ACC, and stores the result back in the ACC. So again, subtraction, even though is doing subtraction this time, but the working is basically the same, that my result will be stored back in the ACC. So instead of adding the values of this address with the contents of ACC, this time around I'm subtracting the contents of this address from the contents of ACC and storing the result back in the ACC. Now let's talk about increment. No, let's talk about the jump conditions. Now the first instruction we see here is jump followed by an address name. Now what does this do? Jump, in this jump instruction, this is known as an unconditional jump. Now what does that mean is that for this jump to be carried out, I'm not doing any comparison beforehand. I'm not doing any if condition, or I'm not deciding or that whether I'm supposed to be jumping or not. This is known as an unconditional jump. So that if I reach an instruction that has jump JMP as the mnemonic, I will simply jump to that address given in the opcode. No conditions asked, no questions asked. Simply, I will jump to this address. This is known as an unconditional jump. However, if I'm carrying out a conditional jump, then conditional jump will be carried out only after I have done some sort of comparison. So how do I perform a comparison? I can do comparison in 2 ways. Now, by the way, what does comparison mean? So basically, I'm checking if the value contained in this address is the same as the value of my ACC. That is my comparison. And in many applications, I can use this simple comparison to perform many conditional jumps. So you can say that it's sort of a way of using the if routine that we use in our high level programming language. So here is sort of you can say that it is assembly language's if statement. So we have to do some sort of decision making, and this is what we're doing. We're deciding whether or not a particular value is equal to the contents of ACC. Now, in this particular instruction, what we're doing is that I'm comparing the contents of this address with the contents of the ACC. They could be equal or they won't be equal. That's the only situations that they could be either equal or not. Okay. Similarly, what this instruction does is that instead of accessing some memory address, I'm simply comparing this value as it is on its own because it's a value hash. I'm comparing this value with the contents of the ACC. So two ways of doing comparison: the contents of an address compared with the ACC, or this value on its own compared to the ACC. The comparison can have two outcomes: either they will be equal or they will not. And based on that comparison, I can decide on whether I'm jumping or not. Okay. Now we've got two conditional jump mnemonics mentioned here. One is known as the JPE, the other is the JPN. Now, what does JPE mean? JPE means jump if equal to. So basically what that means is that if my comparison, if I want the jump to be carried out after a comparison result turns out to be equal, then I will use JPE. So if I want to jump only when two values are equal, then what I will do is first I will compare the two values using either of these two methods, and then I will jump because they are equal. I will jump this there because they're equal. I don't have to jump always because of they're equal. I could choose to jump when they're not equal as well. But let's just say that I want to jump based on two values being equal. So if I'm jumping based on an equality, that means that my mnemonic will be JPE. So JPE is jump if equal to. So what, first of all, I will, since these are comparison, these are conditional jumps, that means they are followed by always a comparison. So if my comparison is equal and I want to jump on an equal, then I will mention JPE. I will use the JPE mnemonic. However, if I do a comparison and I want to jump if it is two values are not equal to, in that case, I will use JPN. Now, when will it be equal to jumping? When will it be not equal to jumping? This largely depends on your problem at hand and how you write it, because you're in control of whether you want to jump on equality or you want to jump on inequality. Now we will be looking at examples ahead that will be making use of these jumping statements to make things much clearer. But again, this is up to you, that should I be jumping on equal to or jumping on not equal to? That's completely up to you, and that your decision should be based on the problem at hand. However, whatever jump you choose, whatever conditional jump you choose, JPE or JPN, you will have to first of all do a comparison. And comparison can be done in two ways, either through direct addressing or immediate addressing. That's it. And if I want to jump unconditionally, no comparison it has been done before, I can do it with this unconditional jump. It does not require any comparison. Simply, if you hit that line, you will jump to this address, no questions asked. Likewise, this is where we can see further examples of your mnemonics. Now, as you can see here, we've got two mnemonics, in and out, and with these are instructions with no operand. I mentioned this a little while ago, and I said that there can be some special instructions that do not require memory addresses, and they do not require immediate values as well. They don't require an operand. This is that example. So as you can see here, in and out, they are perfectly valid instructions. But as you can see here, they don't require any operands. So these instructions are complete without operands. So simply look at the opcode, and what it will do is that if, say, for example, I use the in opcode, what this will do is it will require the user to enter a key. So enter a button on the keyboard. The ASCII value of the key that was just entered will be sent to the ACC because of this instruction. So let's just say this instruction was running and it was expecting the user to give some input. The user entered this small letter A. Based on that small letter A, the value 97 will be sent to the ACC because the ASCII value of small letter A is 97. Similarly, my ACC will have some ASCII value, And if you do an out command, basically what that does is that it prints the character whose ASCII values was just stored in your computer and prints it on the screen, or in your ACC and it prints it on the screen. So again, out does what? That my ACC has some ASCII value in it, and simply I will print the character whose ASCII value is stored in the ACC. So in takes an input and stores the ACC value in the accumulator register. Out takes the contents of ACC and assumes that they're an ASCII value and prints the character that there is present on the screen. So this is what in and out does. Afterwards, I've got bit manipulation operation. And means basically I'm doing an AND operation, in which basically AND operation means that every bit, if it's true, then output's true, otherwise it's false. So if I do an AND hash N, that means that I'm performing an AND operation of the contents of my ACC with the binary representation of this value. So that will allow a bit by bit AND operation. Similarly, if I want to do AND operation with in direct addressing, I can do it with this line here. So what that will do is that it will take the contents of this address. Of course, they will be in binary. They will be brought into they will be done an AND operation with the contents of ACC, and the result will be stored back in the ACC. So first of all, you will access the memory, this memory location, and those memory that data should be in binary. That binary data should be performed AND with the contents of the ACC, and the result was stored back in the ACC. Similarly, we got XOR hash N, in which I've got this value N, and that value in binary will be performed, XOR operation will be performed with this binary value and the ACC. Obviously, this is not binary. How do we know it's not binary? Because it should say B before it. This is binary. But if it goes to ACC, or if it's used in a machine, obviously it would be ones and zeros. So XOR hash N means that I'm performing an XOR operation with the binary representation of this value N with the contents of my ACC. And of course, result will be stored back in the ACC. Similarly, I can do the same thing with direct addressing, in which the contents of this address will be done, an operation will perform with the contents, the OR operation will be performed with the contents of this address and the contents of ACC, and the result will be stored back in the ACC. Same thing with the OR and OR at direct addressing mode or immediate addressing mode. Similarly, we got two other opcodes, LSR and LSL. LSL means logical shift left, and every place you shift left of a binary value, your system will double the value. So for example, if I was sitting at 42, my binary left shift will cause it to go to, sorry, it will, my bit is sitting at say 32. When a binary shift left caused that same bit to enter 64. So basically every left shift caused the value to be doubled. Similarly, logical shift right means that my value is halved. So if my one digit is under say 32, when I move to the right, my value will remain 18. So my on bit was on 32. When I move to the right, it will now be 18. So sorry, 16. So this is how my logical shifting is taking place. Finally, just a quick recap of what the difference between symbolic addressing, relative addressing, and absolute addressing was. Absolute addressing means the address that I'm using I will use the actual name of that address, the numerical value of that address. I will use that. Similarly, as you can see here, the instruction says LDM hash 0. Of course, this is not hash 0 is not an address here, but it will do what it's supposed to do. It will take the value of 0 and send it to ACC. However, in the next line, you see STO210. Now, what that means is that I will store the contents of the ACC and I will bring it to my location I will store it in 210. Now, the same thing is happening with 202 here. 202 is referring to this address over here. So this is absolute addressing. Now, the problem with absolute addressing is that the memory locations that I am using in my code may be available to me when I run the code right now. So the addresses for S210, which I'm using in my program, and 202, which I'm using in my program, they're all available to me for this current program running. But that's not always the case. It might not be available the next time. So that's why if I'm running the code again without having access to these addresses, that means I will have to rewrite the code. Say, for example, my 210 has now become 310 and my 202 has now become 302. In which case the assembly program has to be modified to accommodate for these new changes. Now, this is not a good approach. Every time you load the program into memory, it goes to a new location, because of which this program will become obsolete every time, and you'll have to modify it to hold the contents of the location you are at right now, okay, the addresses you are at right now. So that's not a good approach. On the other hand, if I follow, say, symbolic addressing means that I make use of English type variables. So they mean some, they're not actual addresses. These are actual addresses. On the other hand, I'm using what you call it symbols. Symbols are assembly languages way of saying that they're variables. So we understand what a variable is. The contents will be changing, and once you write a code, you can accommodate that variable to hold different values at a time and longer reusability, as opposed to having to rewrite the code every time it's loaded into the wrong memory location. Now this time I'm using my brain, I'm using structure, I'm using symbolic addressing to make sure that even though I'm not using absolute addresses, but my data still arrives at its destinations as intended. Now what a symbolic addressing does is maintains a symbol table. So for each symbol table, it maintains that what symbols are part of the process. For example, this program has your symbols start, a, loop, so like so. So we got these different symbols. Now for each symbol, a symbol table is created, and a translation process for this logical to physical address will take place whenever the code starts to run. So I can't work with A. My computer won't understand what A is. But if it is converted into actual physical address while it's being used, not while it's being programmed, but while it's being used, then it will not really need to refer to a symbol table to where to go to. Basically, it will simply look at where this A is. Say it says 210 here, by the way. So instead of using A, the translation process will cause A to now look like S210. And any other variable that you choose will take up a physical address. So likewise, this whole program is now written here with symbolic addressing, and each symbol is maintained in what is known as symbol table, and the symbol table is actually guiding you towards the real, or the running program with the real location in the main memory. It's very important that symbolic addressing has to be carried out with the same rule as any programming language, that unique variables and so on and so forth. If there are any restriction on variables, the length of variables, then you have to abide to it. AI is after all a very old language. Okay, then in the between we got relative programming. Now relative addressing. Now what relative addressing does, if you remember, is that it relies on a base register. Now base register will hold the address of the first instruction. So let's just say, okay, my base register has the value 100 in it. So that means that my program will have the first instruction, this one right here, loaded at address location 100. So, and second thing to note here is that when we program in assembly language and most programming languages, all programs are to be handled as one unit. So if Say for example, I've loaded my program at say index position 0, and every other line in my code will be starting from that position. So as it can be seen here, that I start execution from whatever, say 100 location. So my actually address, this line is not at 0, but in fact is 100. And how did I get 0? It says 0 places from the start. So basically, since it is the start and I'm not going any places from here, so that means my address, my base address will be 100 because my current loading position of this program is 100. And every time I discover a new address in this addressing scheme, I will notice that it's relevant to my base, my primary, my first line. So you can see here, this line says store BR register transfer notation BR plus 10. So basically what's it doing is that it's asking you to store the contents of ACC to this location wherever it is. Now similarly, if I use this, that means load the base, the contents of base register and add them by the 1. As you can see here, this is actually doing what? This is referring to these addresses. Now assume that my base register started at 200. So that means according to this address will become 200, the contents of base register 200 plus 10, which means 210. Similarly, this will become 200 plus 2, 202, and so on and so forth. If my base register has the contents, say 300, then you can see that everything changes here. This will become 310, this will become 32, sorry, this will become, yes, 300, 310, then will become 302, so on and so forth. So you're actually basically calculating the address on the go during runtime. And what that does is that it creates a lot of flexibility. Now my assembly language program can be developed easily, and then it can be run just by referring to your base register. Okay, here we can see a few symbols that we're using here: ACC, IX, hashtag, so on and so forth. I've actually mentioned this before, but when we're talking about ACC, we're talking about the accumulator. This is index register. This means that we're using immediate addressing, and the value that it's linked with, written with, is not an address, it's actually a value. B represents that the value written here is written in binary. If it's mentioned with an what you call it at ampersand sign, it means that it's a hexadecimal value. So for example, this you can see here, B, this is actually 0, not a no. B01000101. That means that this value written here is in binary. Similarly, this ampersand symbol means that this is a hexadecimal value. So, and if no symbols mentioned here, neither ampersand or binary, then that value is to be treated as a denary. This address is used for either an absolute address or a symbolic address. So I can see here, whenever we're talking about addresses, they usually mention with this symbol over here. Okay, now let's talk about how this assembly language can be used to solving problems that we were normally doing with some high level syntax, right? So when writing a solution for a problem using low level, we need to break down the problem into simple steps that can be programmed using the instruction set available. One approach is to think in terms of basic constructs we discussed for high-level language. So for example, as you can see here, in this column, we're mentioning all of your high-level constructs that we're familiar with. And this column represents how this statement can be written in using assembly language. So what this line does is, if you remember, this is an assignment symbol. This assignment symbol will cause this value to be stored in A. So because of this line, the contents of A will become 34. So how do I use that for assembly language? We can do something like this. First, I will load 34 into my ACC using immediate addressing. Now 34 is in my accumulator. And after that, I will simply store A. Now what that does is that stores the contents of the accumulator, which are, by the way, 34, into the address A. This is symbolic addressing being used right here. So the contents will be stored in A. Similarly, this is a counting process We were familiar with counting. And what this does is that it increments the value of B by 1 and stores the contents back into B. So what's happening here is that I'm loading B. The contents of B are now in the ACC. I will proceed by incrementing the ACC, and then I will store the contents back into B. So as you can see here, B plus 1, that is incrementing, and result is being stored back in B. This line is written as first load the contents of B, whatever they are, into ACC. Now they're in the ACC. After this line, the contents are in ACC. Increment the ACC by 1, of course, and then the result is stored back at B. So now I have an incremented value stored back at B. Similarly, if I have this over here, what this is doing is that is adding the contents of B and A, and then storing the result back in B. So how that's done is that, first of all, I will load B. I will add A. Now, if you remember, we discussed this a little while ago, that add A means that the contents of this address will be added with the contents of the ACC, which after this line were B. So the contents of A will be added to contents of B, which after this line, sorry, contents of C, which after this line are actually B. So after this line, I'm basically adding B plus A, and then after that, I will store the contents of ACC back in B. So I repeat, load the contents of B to the ACC, add the contents of A with the contents of ACC, which hold the value of B, by the way, and store the result back in the ACC. This, by the way, add does that. It adds this value to the contents of the ACC and stores the result back in the ACC. And when that is done, I will proceed in storing the contents of ACC to make the value updated in B. So like it's done over here, I will add B with A and store the result back in B so that this previous value is gone. So that again, that's happening here as well. That when I do this, store B, the previous value of B will be overwritten. Now this is interesting. What's happening here is that I'm storing the negative version of B into A. So my A will have negative value of B. So I'm basically making the value of A into negative. Now, pretty straightforward statement for assembly language, sorry, your high level language. It looks something like this. But in assembly, the procedure is slightly different. As you can see, it's a low level programming language. In all the examples you see, my one line is in low level will result in 2 or more lines in high level. So these instructions all require 3, this requires 2, this requires 4. So that is the that is the obvious difference you can see here with respect to low level versus high level, that my low level instructions are obviously more than my high level instructions. Now, how is this problem tackled? I will load the contents of A into the ACC. So that's brought in this, the contents of A are brought into the ACC. I will do an XOR with FF, the hexa value of FF. By the way, FF written in binary is actually 4 ones, F1, 4, one F is 4 ones, another F is another 4 ones. So FF is basically all ones. And this FF is basically 255 because every bit, all of the 8 bits are on. When I turn all of the 8 bits on in an unsigned number, that means 255. So what happens when I do an XOR with all ones? Now this is interesting. Let's assume that the contents of A are, say, 10. Now I will make 10 in front of you. So 10, I've got, by the way, 1, 2, 4, 8, 16, 32, 64, and 128. These are the weights for 1 byte. Our goal is 10. So we turn this on, and this on, everything else is off, like so. So let's just say, following this rule, I will turn this 10 into -10. Let's see if it works. So first line says that load A into ACC. So let's just say this is A, it has 10 in it, and I have just loaded this entire byte into the ACC. After that, do an XOR operation with this bit mask. So that means I will have 1, 1, 1, 1, 1, 1, and 1, and 1 right here. Okay, if you remember what XOR does, it inverts that it results in one output if two bits are different. So as you can see here, 0 and 1 are different, the output will be 1. This is same, output 0. This is different, 1. This is same, 0, 1, 1, 1, and 1. And after that, I will have to do what? Now, this is the contents of my ACC. I'll write it here. My 1, 1, 1, 1, 0, 1, 0, 1. So exact same value written here. This is the contents of ACC right now, because all of this operation has taken place in the ACC. Result is stored back in the ACC. This is the contents of ACC right now. So after this XOR operation, my ACC has this in it. Afterwards, it says increment the ACC. So basically, it means I add 1 to it. I will do 1 over here. Resulting in what? 0, 1, 1, 0, 1, 1, 1, and 1. Now, if I do some calculations, you will realize that this is actually -10. Now let's find out. This is 10 right here. 0, 0, 0, 0, 1, 0, 1. This is 10. And this should be -10. So if I add these two values together, 10 plus -10, technically the result should be 0. Let's find out. I've got 10 over here, 0, 0, 0, 0, 1, 0, 1, 0. And let's check this out. This is -10, as you know, it looks like it's supposed to be -10. Let's find out. 1, 1, 0, 1, 1, 0. So if I add this, my result should be 0. Let's find out. 0, 1 plus 1, 0, 1 carry. 1 plus 1, 0, 1 carry. 1 carry plus 1, 0, 1 carry. Again 1 plus 1, 0, 1 carry. 0, 1 carry. 0, 1 carry. 0, and this 1 will be lost in overflow. So my actual result is all zeros, which is 0. So therefore, this in fact number generated following this sequence of events, namely first load the contents of A. You notice that we brought in 10 into the ACC. We did an XOR operation with the bit mask FF. That's what we did here. This is the XOR operation right here. This is the result of that XOR operation. After that, you increment the contents of ACC, which are these, by the way, by 1. And we can see here that we did that over here. And this is the resulting value. And this resulting value should be -10. And we checked that out as well. We added this value, which is this one, with the binary representation of 10. This is 10, and this is -10. And when they were added together, the result was 0. So hence proof this is really -10. And once that is done, this is, by the way, this right now, this is the contents of ACC, by the way. This is the final contents of ACC. This -10 is the final contents of the ACC. After increment procedure, this is what's left in my ACC. After that, store the contents back into the A address A. Now, if you remember that we have to convert it into negative and update the value back into A. So this storing back into the A is done by this line because of this line. So my A will now have this in its contents in binary, of course, because it's being stored on a computer. Okay, just a recap that this method we just covered, if you look closely, this is actually your two-step process for converting a negative number. The first process, if you remember that we studied this in class as well, the first step involves converting the number, inverting all bits. You got the number in binary, we invert all bits first. That's known as the ones complement. So basically this line, as you notice, that inverts everything. So if I have, for example, 10 here, 0 0 0 0 0 1 0 1, yeah, this is my 10 here, 2, and this is 8, yeah, this is 10. So if you perform this 1 1 1 XOR, this is actually the ones complement step in which every bit is just inverted. So as you can see, just pay attention that simply XOR does what? The 0 1 will become 1, this will become 0, then 1, then 0, then 1 1 1 and 1. All the 0 became a 1, the 1 became a 0 0 1 1 0 0 0 0 1 1 1. So every bit got inverted. So this is basically taking the ones complement in which every bit is simply inverted. After that, this step right here, this is getting the twos complement. And if you remember, getting the twos complement means that I simply add 1 in the least significant side, and the resulting number, that is this one right here, will actually be the negative version of -10, which we just checked is really that thing. This is 1 0 1 1 1 1. So this is -10. So this is just the representation of that method, that two-step process in which we should convert the binary number into its ones complement by inverting all bits, and then simply adding a 1 to the least significant side to get the twos complement representation. We are familiar with the method that simply start converting a number. For example, I have this number over here. We simply start converting the number from the right, and any number, if you get a 0, we are familiar with this method. It's easier. We take the right side, we take a 0, we write a 0 back down. We see a 1, we also write the 1 down. But since it's a 1, after this 1, every bit has to be inverted. And you can see here, this is the same number. Now we're familiar with this representation that if it's a 0, write the 0 down. If it's the first one from the right, write it back down as a 1 again. But after that first one, every bit is inverted. This is the method we're familiar with. But in reality, behind the scenes, this step is being carried out. This is a shortened version, but the computer has to carry out this process to create a negative number. So that's why to create a negative number, we have to mention these sub steps as well. So if you remember just a little while ago, as you can see here, basic constructs and to break down the problem into simple steps. So that's what we're doing. We're breaking the problem down into simple steps. Okay, now let's see what the result of these 4 instructions are. So what we're going to do is that we're going to write the assembly language instructions to deal with 1, 2, 3, these 4 instructions. So the solutions for this instruction in assembly language will look something like this. First, we will load 2 using immediate addressing. ACC will have now 2 in it, and then we'll simply store it at A and look address A. This is a similar statement, and that's why it's done in the exact same way. 10 is loaded to ACC, and then 10 is stored back in B. This is a simple addition. First, I load A into the ACC. I will add B with the contents of ACC using this instruction, and that addition will cause the addition of A plus B, and the result will be stored back in C like so. And this is interesting for subtraction. If, say, for example, you allowed the sub opcode, then the code should go something like this. I have, for example, written it here. It could look something like this. So if you are allowed sub, then it's pretty straightforward. You go with LDD A, sub B, and store stod, straightforward. But if you're not allowed to, because some processors may not allow, because I mentioned before that subtraction is not carried out in the subtraction way. Basically, all operations are handled through addition, and that same principle is carried over here as well. So if I want to subtract B from A, what I can do is I can simply first convert this B into its negative version, and then simply proceed towards adding the negative version of B with A. So if you look at this closely, what I'm doing here is that I'm adding A with negative B, and that will show the effect of subtraction. And we can carry off that concept here as well. That first I will find the negative version of B, like so, LDDB XOR F to find the FF to find the ones complement, increment the contents of ACC to find twos complement. Now I have negative B, then simply add A. That will do A minus B. That will reflect the effect of A minus B. And then store the contents of ACC, which are the result of A minus B, into D. And the result will be stored back in D. Okay, let's move on. Now let's see how selection statements that we easily use in our high-level programming languages look like in assembly language. So as you can see on the left side, we have, as the format being used before, that these are high-level language instructions. If you look closely, this is an if statement. What I'm doing here is that I'm doing a compare. I'm basically checking if this condition is true or not. So if A is equal to 0, this is my condition here. Upon testing this condition, if this condition turns out to be true, then this line will run, else nothing will run. So that we don't have an else statement here. So if this condition is true, then this line will run, else you will see no result. Simple as that. Now, how do I reflect that in assembly language? So as you can see here, I start off by loading the contents of A into the ACC. I compare the contents of A with 0, as it's mentioned here. I compare the contents of A with 0. Now, either they will be equal to A, or they won't be equal to A. Sorry, 0. They will be equal to 0, or they will not be equal to 0. Now, think about this. What's happening here? If my contents are equal to A, or if my contents of A are equal to 0, then I'm simply proceeding towards the next line. I repeat this. If the contents of A are equal to 0, then I'm simply proceeding towards the next line. There is no jump here. There is no jump here. I'm simply proceeding towards the next line. On the other hand, if the contents are not equal to A, then I will be jumping here. And in that jump, I will have skipped this line. This is known as a conditional jump. So if this line is true, this statement condition is true, then I'm not jumping. I'm simply proceeding towards the next line. And the jump occurs if A is not equal to 0. So I repeat, jump occurs when A is not equal to 0. And this exact same situation should be reflected here. I load the contents of A, compare them with 0. I load the contents of A to the ACC, compare it to 0. If they are not equal, A is not equal, then I will jump. So I load the contents of A, compare it to 0 if they are not equal. JPN, jump if not equal to. Where? To the end if. I skipped all of these lines. On the other hand, let's see if they are equal. So if say the contents of A are in fact 0 right now. So that means I will load the contents of A, they will also be 0. Compare it to 0, that means they are equal, in which case this is a true, this results in true. I don't jump. So if I load the contents of A, which are actually A, I compare it to 0, will I be jumping? No, I will not, because this states jump if not equal to. But now since the values are equal to, I won't jump, and I will simply proceed towards the next line, which is this block over here, the then block, and do these lines. Now, pay attention to what's happening here. Simple increment statement that we just did a little while ago. Load the contents of B, increment ACC, and store it back into B. But it's very important to know, when are you jumping? Are you jumping on the basis of something being not equal, like we're doing over here? Or are we jumping based on something being equal? So if I'm jumping based on something being not equal, then I've used JPN. If I'm jumping on the basis of being something equal, then I will use JPE, jump if equal to. Now let's look at this second example. If A is equal to B, then I will simply go, if this condition is true, then I will simply go and run this line. However, if this is not equal to, then I will jump, skip this line and come here. So again, am I jumping on basis of something being equal? No, I'm jumping on something being not equal. This statement being true means that they're equal, but they being false means they're not equal. So I'm jumping because of not equal, and that means JPN will be used. Now, the method used here is actually quite complicated. This could be done in a much easier way. I'll explain here. So this is the alternate, much easier solution. You can follow this one. So what we do is LDD A as before, and then what we'll do is simply CMP with B. As you can see here, compare in some examples has been done by simply comparing a value to an address directly to. So what's happening here is that I'm loading the contents of A, and then I am comparing the contents of ACC, which are right now A, with the contents of B. That's fine. You can do that. So basically, you can handle comparison with immediate addressing as well as direct addressing. I'm doing direct addressing over here. I'm directly comparing the contents of ACC with the contents of this address, and that's fine. And from there onwards, the same routine. Am I jumping because of something being equal? No, I'm jumping because of not equal to. So if I'm jumping not equal to, I will do this. So based on that, jump JPN will be handled this way, like this. I will jump if not equal to where else. And if I don't jump, then from there onwards, this code will carry on. So you can say that instead of these lines, these exact lines before JPN, instead of using this, we can simply use these three statements. So instead of these exact statements, I can move on and use these statements. I will. Yes, we can use this statement. This is the right statement. So again, simply do what? instead of these two lines, in fact, these lines over here, all of them, instead of using them, what I can do is I simply go LDDA, compare B. If they're not equal to, jump to else. Jump if not equal to else. So from here onwards, the then statement will continue as it is. So then statement comes here. So my program should go from here like this. This statement over here. So after the JPN as statement, the rest is the same. There's nothing changing here. Now, let's see what's happening over here. In the then statement, I'm supposed to do what? Output the character capital Y. And here I'm supposed to output the character capital N. Now, how is this supposed to be done? Well, in the then statement, I am loading this value into my ACC. Now, what is 89? 89 is the ASCII value of capital Y. So that means after that, after loading 89 to ACC, I will simply proceed towards out, and that will print capital Y on the screen. Same thing is going over here, that if I want to print N, capital N on the screen, I will simply load 78, which is the ASCII value of capital N, to my ACC and simply run out. If you remember, out does what? It will simply print the characters for whom the ASCII value is mentioned over here on the screen. Okay. Now another thing here is that, let's say what's happening here. If this statement is true, then I will run this right here. So that means after doing this, I will skip these instructions and carry on over here. So if you remember, the concept of mutually exclusive statements means that either this code will run or this code will run. So that means this condition can either be true or false. So if it's true, I will run this code. If it's false, then I will skip this code and run here. So that should be reflected as a jump. So if this statement is not equal, so A is not equal to B, then that means this statement is false because A is not equal to B. Then I will jump towards else. That's what mentioned over here. If loading A and comparison B results that JPN, they're not equal, that means I will jump to else. I jump to else. And after jumping to else, I load 78 to my ACC and do an out command, and will be printed on the screen. However, let's look at the other option. If A is equal to B, then what will I do is and if it is equal to B, then that means the statement is true. Then I will come here, I will run this line, and after that, ignore everything that comes after this line. So I won't go to the next line. This is the next line. After this line, no, I will not go here. In fact, I will leave my block altogether. I will come back here. So that means even if this statement is true, then I will be skipping all of these lines and ending up here. So either I'm jumping because this statement was false and I'm skipping this segment and printing this out. Or if this statement is true, then I will run this line and jump and skip this line and end up here. Either case, I'm jumping. So both conditions I'm jumping. Now, if I jumped based on this being false, that's reflected over here. However, if I jump because of this statement being true, that means that I run this line and then I skip all of this part and come right over here. Now let's see what's happening here. If, say, my statement this was equal and this is true, then I will come here. I will load the ASCII value of Y, which is 89, to my ACC, and I will simply output capital Y on the screen. And when I'm done with that, I have to jump all the way over here and skip everything. This should be skipped. So notice what's happening here is that I'm loading 89 to the ACC, I'm running it, I'm printing it on the screen, and then I'm jumping towards the end if. So I'm jumping towards the end if, skipping all of these lines. If I don't jump, then I might end up printing this as well. So for example, if I don't jump, the next thing is that I will also print out the N value as well, because I didn't write jump here. It's very important that if I'm done with this and I'm printing Y, then I should skip everything else and exit to end if. Because if I don't write a jump statement here, then after running this out, I will simply proceed towards the next line which causes me to load 78, which is the ASCII value of n, and print that out. So y and n will both be printed. That's wrong. So I should technically, if I'm done with this, jump to here without printing anything from here.